A Vandermonde matrix is a special kind of matrix built from a list of numbers, where each row follows a predictable pattern. Imagine you take a number, then write it in increasing powers. First power 0, then power 1, then power 2, and so on. That row becomes the building block. Then you take another number and do the exact same thing. Repeat this for all your numbers, and you've created a Vandermonde matrix. The idea feels almost like stacking patterns on top of each other. Each row is like a growth curve starting from the number 1, then rising through higher powers of the chosen value. If you give the matrix 4 numbers, you get 4 rows. If you want a wider matrix, you increase how many powers you include. Everything follows the same rhythm. Each row is the number raised to the power of the column index. This simple construction makes the Vandermonde matrix incredibly structured and predictable, and that structure gives it a lot of power. One of the most important uses of a Vandermonde matrix is an interpolation, figuring out a smooth curve that passes through a set of points. When you want to build a polynomial that matches certain known values, the coefficients of that polynomial can be solved using a Vandermonde matrix. The matrix becomes the bridge between the points you know and the curve you want. One way to think about it is to imagine trying to draw a curve through a series of stakes in the ground. Each stake represents a value you want the curve to match. The Vandermonde matrix takes the expositions of the stakes and arranges them into a system that reveals the unique polynomial passing through all of them. It acts like the master organizer of information. Give it the inputs and outputs, and it solves for the exact pattern connecting them. Another way to view it is through patterns of growth. Each row is a pattern of how the number expands when raised to higher powers. When you put several such patterns together, the differences between them carry information that lets you reconstruct more complicated relationships. This gives the Vandermonde matrix a deep connection to polynomial behavior in general. The matrix also appears in numerical analysis, signal processing, coding theory, and many areas of applied mathematics. Anywhere you need to understand how data behaves when related to polynomial forms, you will often find a Vandermonde matrix working quietly behind the scenes. One interesting property is how sensitive it can be. Small changes in the input numbers can cause big changes in the solutions you get when you invert the matrix or solve systems built from it. This sensitivity makes the Vandermonde matrix both powerful and delicate. In many real-world applications, people use modified or generalized versions that behave more stably for large problems. Despite its sensitivity, the underlying idea remains beautifully simple. You start with a sequence of numbers and line them up so each row shows the number growing through higher and higher powers. The result is a grid that carries a surprising amount of structure and meaning. It demonstrates how powerful simple patterns can be when arranged thoughtfully. In essence, the Vandermonde matrix turns a list of numbers into a rich mathematical object. It reflects how numbers behave when expanded into powers and how these expansions interact with one another. That interaction lets us build curves, decode signals, approximate functions, and solve all kinds of problems where relationships between points need to be expressed in a clear algebraic form. The magic of a Vandermonde matrix lies in how something so straightforward, a sequence of rising powers, can lead to such versatile and far-reaching applications.